Hello everyone. In this week's lecture, we will cover traffic assignment. There are different models for traffic assignment, but before going into the actual modeling of traffic assignment, let's go over some of the basics and introduction of what traffic assignment is and what is it for and how does it work. So as you know, traffic assignment is the final step of the four-step modeling procedure. The aim of traffic assignment is to specify flow features on the network, more precisely traffic volumes and link travel times. The question of interest in traffic assignment is how travelers will be distributed among the possible passes. How will travelers choose routes between an origin and destination? So in the traffic assignment model, what is given? We will be given a graph representation of the network. What else is given is the associated link performance functions. In a static traffic assignment, the link performance function is something like a BPR function, the volume delay function. In a dynamic traffic assignment, it's the fundamental traffic flow diagram. And the third element that is given in traffic assignment is the origin destination demand matrix. Now that we have these three elements, the outcome of a traffic assignment model is the link volumes and link travel times on every link in the network. Before going further into traffic assignment methods, I would like to introduce the notion of user equilibrium. Under user equilibrium, each traveler seeks to minimize his or her own travel time, going from an origin to a destination. The assumption in user equilibrium is that travelers have perfect information about the travel time on every alternative route between an origin and destination. So in user equilibrium, travelers would shift routes if they could save travel time. Therefore, at the equilibrium, there is no advantage in shifting routes because all the routes between a particular origin destination that are being used have the exact same travel time. In other words, any route between a particular origin and destination that is not being used at the equilibrium must have a higher travel time than those routes that are being used. This is also known as the first principle of Wardrop's equilibrium. There are a few basic notations in traffic assignment modeling that we will frequently use in this lecture. Capital N represents the set of nodes in the network. Capital A represents the set of arcs or links in the networks. Capital R is a set of the origin nodes, therefore R is a subset of N because it's a set of nodes. Same with destination nodes, that is represented by capital S. Capital S is a subset of N. Capital A, RS is a set of passes connecting origin, destination, R and S. XA is the link volumes or flow on link or arc A. Small ta is the travel time of link A. FKRS is actually the flow on path K connecting origin R to destination S. QRS is basically the demand between origin R and destination S. And there is an indicator variable represented by delta AKRS, which is 1 if link A is on path K, and otherwise it's 0. To give you a better picture of what do I mean by passes and links and origin and destinations, let's have a look at this simple example where we have 4 nodes in the network. We have node 1, 2, 3, and 4. We also have 4 links or arcs in the network, link 1, 2, 3, and 4. Between node 1 and 3, there is only one path, which includes link 1. However, between node 1 and 4, there are 2 possible passes. One includes link 1 and 3. The other pass includes link 1 and 4. Same story with link 2 and 3. There's only one path between link 2 and 3. That includes only link 2. but between node 2 and node 4, there are two possible passes. One includes link 2 and 3, the other one includes link 2 and 4. Therefore, we can create a matrix of the indicator variable where the rows represents the link numbers and the columns represents all the possible passes between every origin and destination. So in this case, in this network, we have a total of 4 links and 4 possible passes, 2 possible passes between 1 and 4 and 2 possible passes between 2 and 4. Again, for simplicity, I'm not including the short passes between 1 and 3 and 3 and 4 separately. But let's have a look at this indicator variable matrix. So the first column represents one of the passes, pass number 1, between node 1 and 4. So the first pass that connects node 1 and 4 includes link 1 and 3. So therefore, link 1 is 1, 3 is 1, but 2 and 4 is going to be 0. How about the second pass between 1 and 4? It includes link 1 and 4. So link 1 is 1, link 4 is 1, but link 2 and 3, it's going to be 0. How about the first path connecting 2 and 4? It includes link 2 and 3. So 2 and 3 must be 1, the other ones is 0. The path connecting 2 and 4 includes link 2 and 4. So 2 and 4 are going to be 1 here, and 1 and 3 are going to be 0. To achieve user equilibrium, there are a few conditions that need to be met. So here is a simple example of a two-link network, link 1 and link 2, between a single origin and destination. First of all, x1, if you remember, represents the volume of link 1, and x2 represents the volume of link 2. QRS, QOD, represents the demand between an origin and destination. So the first condition is that x1 plus x2 must be equal to q. This is basically the conservation law, that if we have 10 vehicles going from an origin to a destination, no matter what route these will take, the sum of them on all the routes they're taking must be equal to 10. No vehicles will disappear or appear from nowhere along the way. So x1 and x2 must be x1 plus x2 must be equal to q. The other condition that needs to be met is the wardrobe principle, saying that if x1 is 0 and x2 is greater than 0, that means definitely T1 is greater than T2. The travel time of link 1 is greater than the travel time of link 2. Why? Because travel time of link 1 is greater than travel time of link 2. That's why no one's using it, and all the traffic will go through link 2. Same the other way around. If x2 is equal to 0 and x1 is greater than 1, that means definitely T2 is greater than T1. The travel time of link 2 is greater than travel time of link 1. That's why no one is using link 2 and everyone else is using link 1. However, if both of the link volumes are greater than 0, x1 and x2 are both greater than 0, that means the travel time of link 1 and travel time of link 2 must be equal. And the last condition in the equilibrium is the non-negativity condition, which says x1 and x2 must be equal and greater than 0, because we can't really have negative values for link volumes. To better understand the notion of user equilibrium, let's now go over activity 7.1. Activity 7.1 provides you with a little bit more detailed information about user equilibrium and Wardrop's principle, with a nice little example of a tree-link network, as you can see here, from an origin to destination, route 1, route 2, route 3. For every route, we can plot a volume delay function, a volume delay curve. And one interesting mathematical property of user equilibrium is To get that equilibrium flows, the sum of the areas under the travel time versus flow curves must be the minimum. So if I come to this example, and if I pick different flow values on each curve, the sum of the areas underneath each curve, if I sum them up, that has to be minimized. So please go over this 2-page activity, and we'll take it from there and we'll discuss more about user equilibrium later. We now review the mathematical formulation of the user equilibrium problem. As you saw in the previous activity, the user equilibrium flows can be obtained by minimizing the sum of the areas underneath the travel time flow curves. So here we specify an objective function in this optimization problem for user equilibrium. So we want to minimize that z function, which is the summation of the areas under the travel time flow curves. This integration represents that area underneath the curves, where we have an integral from 0 to xa is the link flow, and this ta is the travel time function. Subject to a few constraints. The first constraint is the conservation law, where the sum of the flows going from R to S on multiple passes must be equal to the demand going from R to S. This is a non-negativity constraint, where the flows on the path K going from R to S must be equal or greater than 0. And the last constraint gives you the link flows, which is the summation over all the origin, all the destinations, and all the passes of the pass flows multiplied by the indicator variable, that 0 and 1 matrix that we went over a few minutes ago. So now it's a good time to go over activity 7.2 to learn more about this mathematical representation of the user equilibrium problem. Consider a two-link network as shown below. This network represents one origin-destination pair connected by two alternative routes, as you can see in this graph. Let T1 and T2 represent the travel time on link 1 and 2, and X1 and X2 represents the traffic volume on these links. The total origin-destination demand is represented by Q. What you need to do in this activity is computing the link volumes and travel times at the equilibrium. So as a reminder, the mathematical expression of user equilibrium was we need to minimize the summation of the area underneath the travel time volume curves. So this integration represents that area underneath the travel time function, and this is the summation as we went over in the lecture. Subject to a few constraints, the conservation law constraint, where the sum of the pass flows must be equal to the demand between an RS, the non-negativity constraint, where the pass flows must be equal or greater than 0, and the XA, which is the link flow, must be equal to the summation over all the origin, all the destination, all the passes of the FKRS, which was the pass flow between origin R and destination S, multiplied by the indicator variable, that 0 and 1 matrix. So to solve this problem, let's formulate this objective function. So we have the summation of the areas underneath the travel time volume functions, the summation over all the links. So we have two links, so I have two terms. I have two areas underneath the travel time functions. So the first integration would be from 0 to x1, that's link 1, and the travel time function is 2 plus the volume of link 1, so 2 plus w in this case. And the second term would be the area underneath the travel time of the other link. So it would be the integration from 0 to x2, and the travel time function of the second link, which is 1 plus 2 multiply x. In this case, we put 1 plus 2w. So that's our objective function, which we need to minimize, subject to a few constraints. The conservation law, where the sum of the volume of link 1 and volume on link 2 must be equal to the demand, which was equal to 5. Q is equal to 5. F1 12 and F2 12 must be greater than equal to 0. This is the non-negativity constraint, versus the pass flows must be greater than or equal to 0. So we have two passes going from 1 to 2. Let's call the top one pass number 1 and the bottom one pass number 2. So F going from 1 to 2 must be on each passes must be equal and greater than 0, as it says here. And if you work out this summation of the pass flows multiplied by the indicator variable to get the x flows, you'll end up with x1 is equal to the F112 and x2 equal to F212. But what does it mean? It means whatever volume you see on link 1, it only comes from the pass number 1. Obviously, because there is no other pass, there is no other origin destination in this small example. If we had other origin destinations and other passes, then the link volume of this specific link might be a combination of different origin and destinations and different passes. But in this case, there's only one pass and there's only one link. Therefore, x1 is equal to F112. Similar story with the second pass and the second link. Whatever link volume you see in this link is equal to the pass flow of this specific pass going from 1 to 2. But how can we minimize this function? Obviously, we need to take the derivation. So if you take the derivation here, you'll end up with 2x1 plus 1 over 2x1 power 2. And the derivation with respect to x2 would be equal to x2 plus x2 power 2 equal to 0. To take the derivation, once we take the derivation with respect to x1, and we also take the derivation with respect to x2, and we also have this conservation equation where x1 and x2, if we sum them, they have to be equal to the demand. So we have, if you solve this simultaneous equations, you'll end up with answers where the link volume on link 1 is 3 and volume on link 2 is equal to 2. And because this is at the equilibrium, the wardrobe principle says that the travel times must be equal. So if you put this x1 and x2 in the travel time functions of link 1 and 2, that you'll end up with the exact identical travel times. And that's the property of user equilibrium. So in a small network, we can mathematically formulate that objective function, and in a tractable way, we can solve that minimization and get the equilibrium flows, as we saw in the previous activity. But when it comes to larger networks, networks that have multiple origin destinations, multiple paths between origin destinations, this becomes a little bit difficult. Therefore, we need some algorithms to help us solve this user equilibrium problem. The first algorithm, and the very basic one, is the all or nothing assignment that assumes that congestion has no effect on route choice. And in all or nothing assignment, we assign all traffic to routes on the basis of the shortest path from each origin to each destination, and nothing is assigned to any other route. So what you do is you calculate, based on the free flow travel times, you calculate what the shortest path is between an origin and destination, and then you assign all the traffic to that single path. A little bit more advanced algorithm is the Chicago Area Transportation Study, or CATS algorithm. This algorithm was first developed in the Chicago area for a study of the impact of congestion in the network a couple of decades ago. The CATS algorithm involves a sequence of all or nothing assignments. So what it does is the flow from one origin is loaded into the network using an all or nothing assignment in one single iteration. In the next iteration, we go to another origin node, and then we do another all or nothing assignment. But at the end of each iteration, we update the travel times based on the link volumes. So the flow from one origin node is loaded using an all or nothing assignment in each iteration. The link travel times are then updated, and the next origin is processed. But some flaw in this algorithm is that depending on what origin node you start with, or depending on the sequence or the order of the origins that you want to pick and do all or nothing assignment, you may end up with different results. A better approach is incremental assignments, which involves loading a portion of the origin destination flows in each iteration and then updating the link travel times. The next incremental flow is then assigned to routes on the basis of the updated travel times. So what we do is we assign increments of the demand. For example, if we have 10 travelers, we start by loading 2 travelers in the first iteration. So we assign one increment, let's 2 out of 10, to the network using the shortest passes. Then we update the travel times on the links based on the new volumes. And then we assign the next 2 travelers. We update the travel times. In the next iteration, we assign the next 2 travelers. So incrementally, we assign all the demand to all the passes in the network. If we choose increments to be small enough, it has been shown that the result of the incremental assignment will be very close to the user equilibrium solution. But if the increments are too little, the algorithm will be very time-consuming and computationally intensive. So there is going to be a trade-off between how much does the time or computational power takes to run the algorithm versus how small my increments should be, or how close do I want to be the solution to the user equilibrium. Let's now go over activity 7.3 to get to know these algorithms better. So in this activity, we will apply the incremental algorithm in a small hypothetical network, assuming 20% loading increments. So we have a network from one origin to one destination. There are 3 different links or 3 paths between origin and destination. T1, T2, and T3 represents the travel time on each link. The travel time function of each link is given, and x1 and x2 and x3 are the link volumes on link 1, 2, and 3. And the summation of all the link volumes is equal to 10. That means 10 is the demand, the number of travelers going from this origin to this destination. So to apply the incremental algorithm, we can start with a simple table where we have every iteration listed, and we have the travel times, the incremental assignments, and the link volumes. So let's start with the travel time on the first iteration. In this iteration, because we haven't yet assigned any traveler to the network, all the link volumes are 0. So the travel times will be the free flow travel time, so T1, T2, and T3. If I come to the travel time functions here, x1 is 0, x2 is 0, x3 is 0, so all this is going to be 0, so I end up with the free flow travel times, which is 10, 20, and 25. So I write them down here, 10, 20, and 25. So in my first iteration, I need to incrementally load 20% of the demand. The demand was 10 travelers, so 20% of 10 is 2 travelers. So what is the shortest pass between an origin and destination in this example? Is the one that has the lowest travel time. So link 1 has the lowest travel time, which is 10 units, whatever, minutes or whatever time units. And my incremental loading is 2. I assign these 2 incremental loading to link 1. So I end up at the end of the iteration 1, link volume on link 1 is 2, x2 is 0, and x3 is 0 as well. So now we can go to the second iteration. Now, because we have some volumes on the links, we can update the travel time. So the travel time of link 2 and link 3 still remains the free flow travel time because their volume is still 0, but the volume of link 1 has changed. So I can put this x1 into the travel time function of link 1 and get the new travel time for link 1. So if you do that, you end up with 11.5 minutes, or again, any time units. Now it's time to load the second increment, another 2 travelers to the network. Let's see which one is the shortest pass. Still link 1 is the shortest pass. So my second increment of loading will also go to link 1. So it makes the total link volume on link 1 equal to 4 because we had 2 from iteration 1. We added another 2 from iteration 2. So the total link volume on link 1 is 4. But still link volume of link 2 and 3 is going to be 0. So now, because the link volumes have changed, mainly the link volume of link number 1, we need to update the travel times. So at the beginning of the iteration 3, we get the updated travel times. Still, because link volume of 3 and 2 is still 0, the travel times won't change. It's going to be 20 and 25, but the travel time of link 1 will change. How can I get this 34 minutes here? Because the link volume of link 1 is 4, I put this 4 into the travel time function. I get the updated travel time from this travel time function of link 1, and it's going to be 34 minutes. Now it's time to add the third increment to the network. But to do that, we need to find what is the shortest path. Now the travel time of link 1 has increased to 34. So interestingly, link 2 now is the shortest path. So the third 2 travelers will be loaded to link number 2. So if I want to calculate the summation of the link volumes, link 1 will remain 4 in volume. Volume of link 2 will be 2 because now we added 2 travelers to link 2. And link 3 still has no traveler. Now, again, link volumes have changed, so we can update the travel times in iteration 4. So again, if you put all these x's into the travel time functions as I talked before, you get new travel times. The travel time of link 1 will remain 34 because the link volume didn't change. The travel time of link number 2 will still remain 20. That's because when you put x2 equal to 2 into the travel time function of link 2, the travel times won't change much. Very little change. So still it's 20 minutes. And volume of link 3 is 0, so the travel time still remains 25. So in this iteration, we incrementally load the next 2 traveler. What is the shortest path? The shortest path is link 2 because it's the smallest travel time. So we add this another 2 traveler to link number 2. So the total volume of link 2 will be 4 because we had 2 before and we are adding 2, so we get 4. Link volume on link 1 is 4 and volume on link 3 is going to be 0. So now because the volumes have changed, the travel times again will change. So you can now get the updated travel times using the travel time function if you put these new volumes into those functions. So and in the next step we incrementally load the last 2 travelers before getting into 10 travelers, which was the entire demand. So still the shortest path is link number 2. So the new 2 travelers will still take link number 2, and it makes the volume of link number 2 6, the volume of link number 1 is 4, and link volume of number 3 is 0. So this is the final result. These are the user equilibrium or close to user equilibrium volumes. And if you look at the travel times, you see that travel time of link 1 is 34, travel time of link 2 is 35, and travel time of link 3 is 25 because it's the free flow travel time. But what was the Wardrop's first principle of user equilibrium? The travel time of the used routes will be identical at the user equilibrium. And you can see it's almost identical. Link 1 and link 2 were used by travelers, therefore their travel times is almost identical, while the other link which was not used definitely has a smaller travel time. A widely used algorithm to solve for user equilibrium is Frank-Wolf algorithm, which was first proposed in 1956. The Frank-Wolf algorithm can be used for solving nonlinear optimization problems, like the one formulated for the user equilibrium problem as we saw in slide number 9. The surprising thing about Frank-Wolf algorithm is that it relies on performing a number of all-or-nothing assignments only. The results from the set of all-or-nothing assignments that it does are then used to determine the equilibrium flows. It is important to note that this algorithm is a proven convergent algorithm. In other words, its convergence has been proven mathematically. That means if the iterations are continued, the results will for sure get closer and closer to the equilibrium flows. But how does this Frank-Wolf algorithm, or in other words, convex combination algorithm, works? There are 5 general steps in this algorithm. We first go over these steps and then we have a look at an activity to learn it better. In the first step, you select a suitable initial set of current link travel times. Travel times or travel cost. Here I stick to travel time for simplicity. Usually the free flow travel time. So you initialize all flows of links. XA is link flows and N is the number of iteration or iteration number. So X flows on each link at the iteration 0 will be 0 and N is equal to 0. It's the iteration 0 and we have the free flow travel time. In the second step, we build a set of shortest paths with the current travel times. So we have the free flow travel times from the previous step. Now we find what the shortest passes are between every origin and destination. Now that we are done with that, we make N equal to N plus 1. In the third step, we load the entire demand matrix to the shortest passes that we found in the previous step, using all or nothing. So we obtain a set of flows on links. We call them auxiliary flows. This is where we end if it was an all or nothing assignment only, but we continue in the Frank-Wolf algorithm to step 4. Now that we have this so-called auxiliary flows, we calculate the current flows on the links as the current flow of the link at iteration n is equal to the link volume of the same link from previous iteration plus a factor called lambda multiplied by the auxiliary flow of the same link. Now, in the last step, we calculate a new set of link travel times based on the flows, because now we have a new volume, we can calculate new travel times. And we go back to the second step. Now that we have the new travel times, we build new shortest passes and then we continue. We do another all or nothing assignment, we calculate the auxiliary flows and then we calculate link volumes. And then we continue this iteratively until we reach convergence. So to better understand this Frank-Wolf algorithm, let's go over activity 7.4. In this activity, we will consider the application of the Frank-Wolf algorithm or the convex combination algorithm to a simple 3-link network as you see here. From an origin A to destination B, there are 3 links, where T1, T2, and T3 represents the travel times of every link, and V1, V2, and V3 represents the link volumes. The travel time function of every link is given. And the demand is also given by the problem. A total of 4,000 vehicles wish to travel from A to B. If you remember from the user equilibrium mathematical formulation, we had to minimize an objective function which was the sum of the areas under the link travel time functions. So we formulate that in this problem, where W is our objective function, and we have to the sum of the integration of the travel time functions from 0 to xi, where xi is the link volume. Now in the Frank-Wolf algorithm, we can replace that with fi plus lambda di. So if we formulate this for every link in the network, so for the first link, I will have the integration from 0 to f1 plus lambda d1 of the travel time function of link 1. You can see it's the same travel time function here. If I take this integration, I'll end up with this formula for W1. If I continue that for all the other links as well, if I calculate or formulate W1, W2, and W3 as I did here, and I sum them up, I have to sum them up, I will end up with this function. And if I expand it, I will end up with an ugly formulation looks like this. To minimize this, we need to take the derivation of this with respect to lambda. So if I take the derivation with respect to lambda, make it equal to 0, I'll end up with a formula for lambda, which is a function of d1 and f1, d2 and f2, and d3 and f3. Now we will use this lambda to create a table of calculations based on the Frank-Wolf algorithm steps. Now we set the calculations in a simple table below, where we have the first iteration and the second iteration every link 1, 2, and 3 in every iteration, and we will specify f, which was the auxiliary flow travel time, y, and d, which is simply y minus f, and the parameter lambda, which we derived the formulation for. So let's focus on the first iteration. The first flow vector f comes from an all or nothing assignment based on the free flow travel times. So looking at this first row of the first iteration, so looking at the link travel times of link 1, 2, and 3, link 1 is the shortest path, so in an all or nothing assignment, all the 4,000 vehicles will be assigned to link 1. Now that I have updated updated link volumes, I can update the travel times using the link travel time functions. So travel times will be updated to 50, 15, and 20. Now I do another all or nothing assignment. This time link 2 has the shortest travel time. So in an all or nothing assignment practice, all the 4,000 vehicles will go to link 2. Now simply d is y minus f. So here I will get minus 4,000 because it's 0 minus 4,000. Here I get 4,000 minus 0. Here I get 0 minus 0. So I get my d for every link. I had my f, I had my d for every link. Now I can calculate lambda using this equation that we derived, which was only a function of d1 f1, d2 f2, and d3 f3. So if I put all these d and f's into that equation, I'll get this lambda. In the second iteration, again I start with calculating f. This time f will be calculated using this formula, which is new f is equal to old f plus lambda multiplied by d. So new f for link 1 would be old f plus this lambda multiplied by minus 4,000, you'll end up with 1,600. F new for link 2 would be f old, which is 0, plus lambda multiplied by d of link 2, 4,000, I'll get 2,333. I do that for link 3, I'll get 0. So now that I have new link volumes or auxiliary flows, I can calculate new travel times. So I calculate the travel times using the travel time functions. Then I do another all or nothing assignment. Here link travel time of link 1 and 2 is equal, but the shortest path is link 3. So in an all or nothing assignment, all the 4,000 flows will go to link 3. And as a result, I can calculate d, which is y minus f. So I calculate that, and because now I have d and f, I can calculate a lambda. So if you continue this in an iterative process, you end up at the convergence point, where travel times won't change much and flows will remain the same, and you will be at the user equilibrium. So I want you to go over this activity again on your own. Take your time, go over the mathematics, use the calculations given in your own working to get this formula, and create this table on your own. Try to calculate this f, y, and d's, and then maybe do another iteration to see what you get at the convergence points.